This talk highlights our continuous in situ analyzers for real-time nitrite and nitrate monitoring and the way in which our analyzers are being used for the monitoring of nitrification events in chloraminated water systems. So in terms of what we're going to cover today, we'll touch on how our analyzers work, the functionality, the method in which they're based upon. We'll highlight why nitrite monitoring is important within chloraminated systems. We'll touch on the advantages of our analyzers and how they're different compared to typical other competitor systems, but more typical approaches such as UV-Vis. And then, of course, we'll cover some case studies and how our analyzers are adding value when considering chloraminated water systems. So if we look at our systems then, the technology, it employs rapid ion chromatography combined with our patented UV LED detection system. And that ultimately enables simultaneous and selective detection of nitrate and nitrite in situ. In terms of the packages then, or the analyzers themselves, as you can see from the images, we have a portable version of the system that can be transported throughout the site, but we also have a more typical configuration with a HMI. It's for fixed install and more suitable for process control, but essentially both systems employ the ion chromatography with the UV LED detection. In terms of performance then, really what we set out to deliver is lab quality, accuracy and precision. So our systems deliver greater than 95% accuracy in situ, and we have an ISO accreditation, and the ISO is 14034, essentially highlighting the analytical performance of the system in wastewater and other water applications. So the system itself then, without going into too much detail, fluidically, this is what's happening within the system. And essentially, the mobile phase is sodium chloride, so completely non-Haz. The sample is introduced into the mobile phase. Everything passes through an anion exchange column that allows for the separation of the ions, and everything passes into our UV LED detection, which has a wavelength of 235 nanometers. And that allows for, or enables, our absorption detection for nitrite and nitrate. So if we look at how our system works compared to a UV-Vis, UV-Vis detectors or probes, they use algorithms to account for matrix interferences, and they require matrix-specific calibration. If we're looking at the discrimination of nitrite and nitrate, as you can see with a UV probe, both nitrite and nitrate absorb within the same region. So that causes challenges, especially in wastewater applications, but in drinking water also there can be turbidity issues or other organics present which can cause interference challenges. In terms of our system, as you can see with the chromatogram here, because we have that separation up front, that allows for resolved selective detection for nitrite and nitrate. In terms of the analytical range then, for nitrate, it's 0.6 all the way up to 500 milligrams per liter as NO3, and for nitrite, 0.05 all the way up to 100 milligram per liter as NO2. So just to summarize the key differences of our technology versus UV-Vis systems, as mentioned, ion separation combined with our UV LED detection allows for simultaneous selective detection of nitrite and nitrate. Another unique advantage of the system is we calibrate the units in our factory, and there's no need to recalibrate on site. And you can actually move the unit from through various matrices without the need for recalibration. We can achieve high levels of sensitivity for nitrite, even in the presence of very high levels of nitrate, because we have that resolved separation. As mentioned, then it's sample matrix independent, so we can actually deploy in fresh water. We can take the unit, deploy in a fully saline matrix as an example, and there's no need to recalibrate, so it's very robust to a changing sample matrix. And there's also no drift or fouling associated with the measurement because we have that separation up front. Looking at the monochloramine or the chloramination application. So why is nitrite important within these systems? Well, nitrite is a key analyte when considering nitrification. Its presence is an indication that that nitrification is taking place. When we look at the American Water Works Association, some figures that they publish in terms of limits. So they define nitrite concentrations of 0.01 milligram per liter as an alert level, and 0.015 milligrams per liter as an action level in distribution systems. So nitrite detection for nitrification monitoring requires really high levels of sensitivity and accuracy. And to date, typically grab sampling is the standard approach. And this can be okay for some situations, but in other scenarios, particularly when temperature variations are present, it can be challenging. One reason is, of course, the labile nature of nitrite. It's unstable, and over time that can change. But also because of the low levels, it's a challenging concentration to detect using certain other analytical instruments. So there's limited options for reliable continuous nitrification monitoring, and that's where our system can add value. So in terms of the data which is generated by the system, we have a proprietary IoT platform called Aquamonitrix, and that allows for communication and interaction with the concentration data in real time. It also allows for the setup of alerts, alarms, and thresholds, and the customer is notified if those thresholds are exceeded. And of course, it allows for remote access to the system as well. So you can remotely modify your sample frequency. You can increase your frequency, or if a threshold is exceeded, you can do an immediate run, etc., remotely. So looking at some case studies, then this is just an example of our unit deployed in a US water distribution system. And here's an example of a nitrification event which is being observed on our Aquamonitrix platform. So as you can see, quite stable nitrite and nitrate levels over a period of time, and then the nitrification event taking place as NO2 creeps up to significantly high levels. The operators were able to, because they had that real-time data, they were able to take action to address the nitrification event by dosing with free chlorine. And here are some other examples which we'd like to highlight as well. Just a similar situation. The customer was monitoring the nitrification events. They had that visibility in real time, and when certain nitrite levels that they established the thresholds that they didn't want to surpass, when nitrite levels got to certain concentrations, they added free chlorine to account for the nitrification event. And this is just kind of giving an example of another customer who were able to take various actions based on the real-time data, the real-time nitrite data. So as the nitrification event started, they cycled their tank. As levels increased to more significant concentrations, they did a more comprehensive deep cycling of the tank, and then they added free chlorine to account for the nitrification event at the end. This is another example. Then in the UK, this particular customer was more using the analyzer as an early warning, and also to ensure compliance was being met. So no significant nitrification events were observed, but it was more just a continuous early warning system there that if something did go, if nitrification event did come in, he had that visibility to take action. Within these traces, then you can see just a number of bump tests which the customer did, and these concentrations were within 95% of the true value compared to his lab-based instrumentation. So this is just another example which we wanted to highlight where the analyzer is being used. So to close then, really just to highlight some of the areas of value where the unit is being used within the chloramination application. So really it's enabling the customer to be early, so the customer can reduce the impact of nitrification through the earliest possible detection. It provides the opportunity to automate, so continuous monitoring offers the possibility of automation for the mitigation of the nitrification event, and then of course to minimize the risk of nitrification occurring at all. As we know, there's significant health issues associated with high levels of nitrite in drinking water, but there's also potential taste and odor issues which can come in the form of trichloramines and so on. But by having that real-time data, it allows for minimization of those negative impacts. So that was just a quick run through. As Mike said, very happy to take some questions and answers at this stage.
Okay then, Owen, I've got a couple of questions have come through. The topic of the webinar was around chloramination, and somebody's asking, how does the monitor perform with regards to varying chloramine levels? Because it's another compound in the water. Chloramine is going to be present in a chloraminated system. So the question was about how does chloramine affect the analyzer? Was the question?
Yeah, it's a good question. So as a side note, in fact, our detector can detect monochloramine, and we have a version of the system that's coming online now, which will allow for the detection of monochloramine in combination with nitrite and nitrate. So that will be released early next year. But I think the majority of use cases in which our analyzer is being used, there's no issues with coelution of chloramines with nitrite and nitrate. We have had on one occasion there was a slight coelution with monochloramine, and there was really elevated levels of organics in this particular customer site. So for that type of environment, we would be deploying the new version of the system. But for the majority of our customers that are using the analyzer, there's no significant issues, or there's no coelution impact associated with monochloramine and nitrite or nitrate detection.
Thank you, Owen. And as is always the case, your answer has prompted another question. So in terms of the available detection ranges, you've clearly piqued somebody's interest here about the chloramine. What for the three parameters we're discussing, what do you feel are the measurement ranges, 0 to what, for the three different parameters? What sort of ranges can we cover?
So for nitrite, it's sub 0.05 milligrams per liter as NO2. That's for nitrite. For nitrate, it's I think it's in around 0.3, 0.4 milligrams per liter as NO3. And for monochloramine, it's sub 0.1. So okay. We're yet to finalize the exact LOQ, but that's the type 0.08, 0.1, that type of LOQ is what we're looking at for the monochloramine.
Another question coming through around the application is, for the data we've seen on the case studies, what was the sampling frequency? What was the measuring frequency of the readings? Yeah,
it fluctuated, or it depends. That was of course dictated by the customer and the application, but typically it's every hour. That would be most common, but we have had some deployments where they would be running more frequently, maybe 30 minutes. But of course, we can analyze every 15 minutes if needed. But generally, it's typically about every hour that they would monitor.
Okay, and then again, related to the case studies, how did the data how was the data transmitted? How did we get hold of the data?
Yeah, so as I briefly mentioned there, we have our own proprietary IoT platform called Aquamonitrix, and that allows for immediate access to the data. So once the analyzer is installed, within minutes, the customer has real-time visibility of the concentration data that's being generated. So for these deployments, the data was communicated via the Aquamonitrix IoT platform.
We've got another one coming in. It's a very straightforward question. What are the maintenance requirements?
Yeah, for drinking water applications, it's very straightforward. I mean, I can't give a like what Mike, you might have some figures, but it's 6 months to a year for drinking water. It's very straightforward. It's an easy environment compared to some of our other deployment sites, such as wastewater and aeration tanks.
Yeah, I think the in terms of maintenance, there's if we break it down to two chunks. There's replenishment of reagents, which is not maintenance. That's a consumable thing. And for this type of deployment with an hourly measurement, you're not going to be changing your reagents any more often than once every 6 months, and probably once every year, depending on which reagent volume you use, because we can supply with a 2.5 liters or 10 liters, so you can run for 6 months or up to a year. So that's a consumables thing, but the actual maintenance on a potable water application, in our experience, again, it's an annual type of thing. You're looking at maybe changing some tubing on some of the peristaltic pumps. It has a lifetime, it needs changing. But in terms of blocking dirt, fouling, things like that, you just don't find it in these applications. It runs for a long time between maintenance. The instrument guy in me never likes to leave things for that long anyway, so I would probably recommend you have a look at it once every 3 months. Whether you have to do anything is another matter. And the other thing which we didn't touch on in the webinar was the IoT platform does have inbuilt diagnostics around lots of different things. You know, there's quite a long list, maybe 10 different things we pick up on and flag, which would be, recommend that you do this rather than have to do it. So you might get a recommended change on a column, or we might pick up a flow fluctuation or something like that. So there is diagnostics built in as well. Hopefully that answers the question. Its simple answer is need to do maintenance 6 months to a year, something at least that order of magnitude. That appears to be most of the questions. Oh no, we've got another one coming through. It's slightly off topic. Excuse me. How does the analyzer perform in groundwater applications? Rather, this is a chloraminated system. It's obviously treated water, but nitrite and nitrite can appear in groundwaters. What's our experience with that? It seems to be the question that's the.
Yeah, I mean, it would be a perfect application. We've deployed in groundwaters a number of times, but again, straightforward application compared to some of our more challenging matrices. Keep in mind, as mentioned, the system can analyze fully saline water. So it's and we monitor within aeration tanks, really challenging, complex matrices. So groundwater, it's a perfect analyzer and the perfect application really for the analyzer. So.
Okay, that's it, I think, in terms of Q&A. If anybody has got a burning question, now's your opportunity. We've got a few minutes left of everybody's time. And if there are no more questions, we're probably going to start the wrap up. First of all, can I just say thank you very much, everybody, for attending. Thank you for the people who've participated and fired questions into us. And most of all, thanks to Owen. I'm sure a lot of us have been on these calls and presented webinars. There's a lot of presentation and preparation goes into it. So thanks very much, Owen, for taking us through the case studies. The session has been recorded and we will make it available to everybody who's registered. You'll get a link to have a look at that. We will also circulate Q&A, the answers. We're going to circulate those so everybody knows. And if anything does pop into your mind over the evening or the next few days, you obviously have our email from the invite. Fire that in and we'll include that into our answers. So it's just remains to say thanks very much, Owen. Thank you very much to the attendees. Watch out for the next one in our series of webinars. And thank you very much. Good evening.